Good afternoon, everyone in the room and everyone online. My name is Langning Huo, and I'm a researcher in SLU in Sweden. But this work is done in Finland in the team that led by Professor Jan Kamara. And we have a special attention to the early detection of spruce by beetle infestations. So why this is important? Why we need to develop some tools for the inspection? And this is highly related to the measure of damage control. So the in-time sanitation cutting is almost the only way that has been shown effective on the population control. So we have this idea that we should detect and remove the trees when the bark beetles are still inside the barks. And what that means, and in this Nordic country, that means we need to detect and remove them from the beginning of the attacks until about 8 to 11 weeks after the swarming. And later than that, the new generation has already swarming and attacking the nearby trees. So we have some photos showing the healthy trees and also the green attack trees that are trees infested, but they don't show any discoloration from the tree crown that can be sensed by human eyes. So this work is also very, very challenging to do it from the field. So we don't see so clearly which tree are under attack if we don't have a detailed inventory. And then a lot of attention has been paid to the remote sensing data. And then this is an interesting research question on how early the remote sensing data can detect these rapid infestations. And there are a lot of work has been done using the satellite images, for example, Sentinel-2. And so far, we don't see very concrete evidence saying that we are detecting the green attack phase, or it's challenging to confirm that what the different signals are causing by the green attacks instead of other information such as the forest structure or even the vulnerability before the attacks. And to solve the problem, we turn the direction of looking at the drone images. We can see here that we can clearly see the individual tree crown and branches. So we only analyze the spectral reflectance from the tree crown without considering the noise information from the canopy gaps. And then I list some study that's almost the only study that exists focusing on this green attack phase. We can steadily see that in overall, they have a very low detectability in this green attack phase. For example, the study we have presented last year in this RESDINET seminar that we showed only 15% of the green attack trees can be detected at after 5 weeks of infestation. And then the detection rate was high after 10 weeks, but that's also the time when the second swarming starts. So that's almost too late for the damage control. And also similar results from different studies. And I think in these scientific discussions, people start to thinking it's time to stop putting more efforts on this. Is that really possible to achieve it? And we see another chance that is using the hyperspectral drone images. They have a much higher resolution and at the same time, much higher spectral resolution. And then that's actually the data that have been collecting in Finland in the Helsinki Central Park. That is the highest spectral and spatial resolution ever used in this topic. So we try to push the limitation to see how this detectability for the green attack phase. And then if this type of method, this type of images, they still can't work for this problem, then maybe it's time to consider changing the strategy. And the sensors, the hyperspectral camera we use, they are to separate one camera covering the visible band to near bands, and another camera covering the sphere band. And in total, there are 448 bands covering from 400 to 1700 nanometer. And we have image at 0.1 meter resolution. Yes, this is a study area that we have 4 times of data acquisition in total, and that's in the late summer. So this is the time covering the second swarm. And we have the temperature data here that is showing the degrowing days. And from the degrowing days, we can assume the second swarming starts around week 27 to 29. So that's our 4 times of data collection covering about 1 to 9 weeks of infestation, and have 2 weeks in between. And we have 56 healthy trees that are confirmed from the field inventory. And then we got 41 infested trees that are visually interpreted from the orthophoto. So the trees do not show any discoloration from the September in 2021, but they kind of suddenly died in the next June. So that's we define that this is in the green attack phase that are covering by our hyperspectral images. And some generic information about tree segmentation, as we can see some example here. We have this automatic segmentation of tree crowns and then matching with reference data. And for each tree, we match them in between the images. So each tree has images from 2 cameras, the sphere camera and linear camera, and 4 times. So one tree needs to be successfully segmented from all the 8 images. That's defined as a successful segmentation. So this segmentation rate is still considered to be high, and we have some examples how these trees look like. And yes, we have a proper design of this study, and that's a lot of information. So I will just pick up the most exciting part to present here. And first, we have a look at these spatial signatures from the healthy trees on the left, covering 4 different times, and the infested trees on the right, covering different time. And the first information or impression we get is that the spatial signature difference between different times, and the difference between times are even more different, even much more different than the health between healthy and infested trees. So this gave us a hint to pay attention to the noise information from the hyperspectral images. That's a common challenges for us to analyze the spectral signatures. And the other one is the phenology. So the trees naturally have this changing of colors and phenologies that we need to consider something we observe changing through time. That's not because of the bark beetle infestation. So instead of going into this, for example, machine learning method, because we have limited number of trees as samples, we start kind of band by band inventory, which bands has the best potential to separate the attack trees and healthy trees. And then here we have this separability of the reflectance by band. And that's passed by the linear discriminant analysis. And that's how the separability differs between the time 1, time 2, 3, and time 4. So time 1 is about the beginning of the attacks, and time 4 is kind of ending and close to the time when the second swarm happened. And again, we have this observation. Some bands, they have really high separability in, for example, time 2. For example, the sphere bands. And feels like they have a good hope to separate healthy and infested trees. But this phenomenon, they don't continue at T3 and T4. So we kind of interpret this type of thing is there are some other information that are in these spectral signatures that's influencing our observation of the decline of trees. But we want to find some bands, they have an increase in separability according to time and according to how long time a tree has been infested and the tree has a decline of the health. And I map here with gray background. That's the bands that fulfilling this requirement, that they have an increase in separability. that have a correlation with the health status of the tree. And some bands in the end of the image collection, they have a good separability around this visible band, around this red edge bands, near bands, and some in the sphere band. And also we have the similar analysis on the first and second derivative reflectance. And they are less sensitive to the illumination changes, and these are commonly used to analyze these spectral signatures instead of noise information. And the first derivative describes the slope of this reflectance curve, and then the second derivative, they describe the slope of the first derivative, and that means it's describing the curvature of this reflectance signature. So by similar methods, we test on the separability between the healthy and infested trees using the first derivatives. And we can see that some bands around 550, they start to be really outstanding in time 4 and time 3. They also have the fulfilling this requirement that they have increasing separability. And it's the same for using the second derivative, and they are even having more or better separability in the end. And then this is followed by the red edge bands. So then we get very curious what is happening with this reflectance around this 550 region. So we have a close look at the spectral signatures between 490 to 560, and 490 is the blue band, and 560, that's the green peak, and reflectance in the middle, sometimes called the green shoulder spectral region, or sometimes called the blue edge. So we use the term green shoulder here. And the first line is a reflectance, and then the second line is a first derivative from time 1, time 2, time 3, and time 4. And we found that this at the first derivative, they have this two-peak structure, and have a dominant peak that's slightly going down after a longer time of infestation. And the subdominant peak, they kind of increase very obviously after a longer time of infestation. So we call these 2 points green shoulder inflection points, and that's describing the first derivative curves and peak values. And if we have a look at the second derivatives, we found there is usually a valley in the curve, and then the valley value increase with longer time of infestation. So we call these curvature points. So maybe we can see around 530 is curvature point. So we can almost see that the healthy trees are more curvy in this area, and the attack ones have become more and more straight. So this is a visualization how these inflection points and the curvature points shift through time. And most obvious, we can see in the second peak, they increase with longer time, and curvature points increase. And then we create these indices. That's by a combination of the value from 2 peaks. And then the x-axis is curvature point value. So you can see the healthy trees, that's the blue dots here, that stay similar values through 4 times. The value from the infestations, they gradually differentiate from the healthy ones. So that's so we propose these 2 indices and to try their detectability on the trees. Yes, so this is a figure showing how these 2 indices change through time. And for the healthy ones, they stay almost stable compared to other indices. And then these 2 values increase a lot for the infested trees at T3 and T4. And in this case, we calculate 2 metrics one is the separability that's tested by the LDA method. And the difference is that, for example, here, the distribution of the healthy trees become very narrow in these specific images. And so there are some separability, we must say, between the healthy and infested trees. But if we look at all the images, we kind of know all the trees at t time 2 is kind of within this healthy range. So when we calculate this detectability, we calculate this threshold from all the images from T1 to T4 on the healthy samples. So we kind of say this is a threshold that can be universal for our study area, our data set. And then if one tree has these indices higher than that, we detect them as infestation. So in this way, we calculate the detectability at time 4, that's around 0.8, and at T3 around 0.3. And we have a comparison between the new green shoulder indices and the existing one. And the top ones, called P or I, they have the best detectability at the time 4 compared to other indices we tried. And but they also use a green shoulder reflectance here. And the red edge bands is commonly used for the vegetation stress. But in our case, the detectability was relatively lower. So so that's the green shoulder indices. And when we calculate it, we still need the hyperspectral drone images to calculate the first and second derivatives. So that means the data are very expensive and very complicated to obtain and to calibrate, and a lot of pre-processing required. So we have this idea that we want to propose some indices that could work for the multispectral camera too. So we want to have indices with a combination of 3 or 4 bands reflectance that are possible for the multispectral cameras too. And that's the case for the satellite images too. So if we use a hyperspectral satellite images that have much lower spatial resolution. And I will not go into details about this, how we simplify it, but it's based on the linear relationship between the reflecting difference of certain bands and to the curvature point and inflection point. So in the end, this is how they are simplified. So we need reflectance from 3 bands. One is traditional used blue band, and the other 550, that's a traditional used green band. And then one additional one we need is this green shoulder bands, 530. Then in this way, we test again the performance and the detectability at time 4 is around 0.8 and about 0.4 at time 3. So they don't decrease the detectability a lot compared to the indices based on the derivative analysis. And then of course, these the sensor we use have really narrow bands, and then we test how it may perform for the bands with a larger bandwidth. And we can see here the accuracy kind of decreased a lot after wider than 50 nanometer. And before within this range, it's kind of working okay. And that's a common range for a lot of sensors, multispectral drone sensors, or even the satellite images. And I list here the planet scope super do satellite images have a 3.7 meter resolution. And compared to the old products, they have an additional band called green 1. And that's exactly covering the new bands that we propose here, the 530. So it's a coincidence or some good luck. So why this green shoulder bands it works? As I correlated with these pigments that are involving in this photoprotection and the photochemical functioning of the plant. And in the 1990s, when these infestation indices were proposed, the 530 was proposed to use the wavelengths for exactly these pigments. And when they proposed it, they kind of try the reflectance from different wavelengths, and then until they find the most obvious or the best linear relation between the pigments and the indices. But now we know that this 530, the special thing about it is value point from the second derivative curve. And also another improvement that we may consider is that some study use the maximum of the first derivative. That means they use the dominant peak value from this. That's 521. And then in our case, we found that it's actually the second peak that are contributing most. So, and why this combination works? So we compare the green shoulder indices and the red edge inflection position. They have been developing for many years. And then if we look at how they calculate, they are actually very similar on this linear interpolation method. And the difference is the red edge bands use 4 points, and then the green shoulder indices we use only 3 bands. And we also know there are many different ways to calculate this red edge inflection position. So maybe and some of them are shown to be better than the others. So we still have hope to further improve this green shoulder inflection position, the correlation of it. And back to our topic, how early can infestation be detected? In this research, we don't have the monitoring on single trees, so we don't know exactly how long time a tree has been infested. We can only know that from the temperature conditions, and we assume that at T3, that's about 5 to 7 weeks of infestation, and time 4 is about 7 to 9 weeks of infestation. And at 9 weeks of infestation, that's the beginning of the second swarm. That's like the first rugby to become adults and kind of fly out. And then there are sometimes maybe several weeks until half of them start to be ready to attack surrounding trees. And since the study is conducted in the same year in southern Sweden, so we also have a comparison between this study and the previous study. And using the hyperspectral images and result from Finland has a much better detection rates covering the second swarming. And there are several reasons we can consider. And about this hyperspectral sensor might be better than the multispectral one. The multispectral one, we don't have this reflectance from 530. Maybe that's the key point. And also the level of intensity of the attacks can also be considered because we have this managed forests in Sweden and nature reserves in Finland. So some future work, we can have more development on this green shoulder region. And this study we are planning to have more study that's especially focused on the red edge bands and also these rear bands which show a good potential, but we will need more steps to analyze it. And then also consider the physiology. That's very important to know when is the time that a tree kind of stop functioning. And then this is the point I always present. We need more study area, more years to know what is concrete, what's the detection range that we can achieve. So this is our study, and I would like to mention this as a teamwork from FGI. There's a lot of efforts that's been put into this data collection and data calibration, so eventually make this analysis happen. So these are definitely teamwork. Thank you.